Imagine, for just a moment, that you are plunging right beneath the surface of the ocean.
Leaving all that bright, windy surface world completely behind you.
Exactly. You slip past these rolling steel gray waves, and instantly you're submerged in this freezing emerald tinted water.
And you're about 30 feet down.
Yeah, 30 feet down. And you can feel the pressure of the ocean. It presses against you, kind of like a heavy blanket of water.
But gently, just letting you know it's there.
Right. And as your eyes start to adjust to the underwater twilight, this breathtaking sight just materializes out of the gloom below you.
This towering golden brown canopy.
Huge, giant leaves, and they're swaying rhythmically, moving in this perfect synchronized harmony with the push and pull of the ocean swells.
And the light from the surface is just fracturing through the waves.
It dapples and dances right through this thick underwater forest. It doesn't just look like a habitat. It feels alive, like it's humming with this wild, hidden energy.
It's an incredible scene.
But now, picture yourself not as a human visitor, wearing a diving mask. Picture yourself as someone who actually belongs there.
A local resident.
Right, a robust rust-red fish. Your mottled reddish-brown scales, they perfectly camouflage you right into the patches of red algae and those golden, fluttering fronds above you.
Just hovering quietly in the water.
Exactly. Your pectoral fins are making these microscopic automatic little adjustments so you stay perfectly still in the rushing current. But suddenly, you feel it before you see it.
The change in pressure.
Yeah. Your lateral line, that sensory organ down the side of your body, it detects a massive change. A rushing wave is coming.
But not a wave you'd see on a beach.
No, this is moving entirely underwater. It's this silent, invisible wall of physical force pulling and pushing straight through the heart of the forest.
And it brings a serious chill with it.
A biting chill. The temperature just drops in seconds. But with that freezing water comes an absolute explosion of food.
A flurry of tiny crustaceans.
Just swirling wildly. So you dart forward, snap up a quick meal, but just as quickly, your survival instincts scream at you to hide.
Because something else felt that wave, too.
Right. You bolt downward, diving into a jagged, dark crevice in the solid granite floor. You hold perfectly still as this massive shadow eclipses the sunlight.
Gliding right overhead.
A 20-foot basking shark. Its mouth is wide open, just filtering the exact water you were swimming in a second ago.
And you're just hiding there, a tiny piece of this roaring underwater metropolis.
It's wild. Welcome back to Saltwater Stories. Today we're traveling to a place that, well, it sounds like it belongs in a fantasy novel.
A world of golden forests and jagged underwater peaks.
But I promise you, this underwater rainforest is completely real. It's entirely hidden out in the open ocean, exactly 80 miles off the coast of Maine.
It's a miraculous spot called Cash's Ledge.
Cash's Ledge.
Yeah, and it's a hidden miracle. What we are exploring today, it isn't just a patch of seaweed. It's an entirely submerged mountain range.
Which is just crazy to think about.
It is. And the people who spend their lives studying how the ocean works, they have a special nickname for this isolated, magical place. They call it the Yellowstone of the North Atlantic.
The Yellowstone of the North Atlantic. Wow.
Yeah, so today, our entire journey is focused on this one incredible place. We're going to look at the architecture of how it was built, the physical engines that keep it alive, and why its survival is so wildly important to the health of the entire ocean.
Okay, so let's unpack the actual geography of this first, because when I think of the open ocean, especially 80 miles away from any coast, I just picture endless, deep, empty blue water.
Right, just a flat, featureless bottom.
Exactly, like a muddy floor hundreds of feet down.
Yeah.
So how on earth is there a mountain range hiding out there? Can you paint a picture of what we're actually looking at if we, I don't know, drained all the water away?
Well, if you could pull the plug and drain the ocean, you'd see that your mental picture of the surrounding area is actually dead on.
Oh.
Yeah. The areas immediately surrounding Cash's Ledge are these deep, dark, muddy valleys. Geologists call them basins.
Okay, basins.
Specifically the Ammon Basin and the Cash's Basin. They plunge hundreds of feet down into what is usually pitch black water. The floor is just fine silt and mud that's piled up over millennia.
Just a dark, muddy wasteland.
Basically. But right in the middle of all that flat mud, just erupting upward, is a 32-mile-long jagged ridge of solid rock.
32 miles long.
Yes, it's a massive, impenetrable wall interrupting the seafloor. And the peaks of this mountain range climb so dramatically toward the sunlight.
So how close do they get to the surface?
The absolute highest peak is this rugged pinnacle called Ammon Rock. And it climbs so high from the dark basin that its tip reaches to within 30 to 40 feet of the sunlit waves.
That is just staggering. I mean, you could be sailing on a boat looking out at the endless ocean, totally unaware that 30 feet below your hull is the tip of a giant mountain.
Precisely. It's an invisible hazard if you're a sailor who doesn't know it's there.
Right, but an oasis if you're marine life.
Exactly. But to understand how this mountain range even got into the middle of a muddy ocean basin, we have to talk about history, geological history.
Okay, I love a good origin story, so we're going way back.
Way back, we have to talk about two of the most powerful forces on the planet, which are fire and ice.
Oh, wow. So millions of years ago, right?
Billions and millions. Long before the Atlantic Ocean looked anything like it does today, the Earth's tectonic plates were shifting, colliding, tearing apart.
The usual chaotic Earth stuff.
Right, and deep underground, unimaginable heat and pressure melted the Earth's crust into bubbling molten magma.
Okay, so it was a volcano.
Not exactly. This magma didn't erupt as lava. It actually stayed trapped deep beneath the surface. And slowly, over vast amounts of time, it cooled down.
Oh, I see.
And when magma cools super slowly under that kind of immense pressure, it lets these large crystals of minerals form and lock together. Things like quartz and feldspar.
Which makes granite, right?
Exactly. It creates an incredibly dense, hard, igneous rock. Granite. It's the exact same ancient rock that makes up the beautiful, rugged coastline of Maine today.
But at the time, this chunk of granite was completely buried underground.
Yes. So for the second half of construction, we travel forward in time to the Pleistocene epoch.
The Ice Age.
Right, roughly 13,000, 20,000 years ago. Back then, the Gulf of Maine wasn't an ocean at all. Global sea levels were way lower because all the water was locked up in ice.
So this whole area was just dry land.
Dry land, completely crushed beneath a colossal sheet of ice called the Laurentide Ice Sheet.
I've heard of that. But when we say sheet of ice, we aren't talking about like a thick layer of frost. We're talking about a glacier that was over a mile thick.
Over a mile thick and spanning across millions of square miles.
That is just so hard to visualize, the physical weight of that. It's like taking an entire mountain range of solid ice and dragging it across the continent.
That's a great way to put it.
It makes me think of an impossibly heavy, slow-moving bulldozer. Just a billion-ton bulldozer scraping the earth, tearing up forests, ripping up topsoil, and grinding regular rocks into powder.
Just through sheer friction and gravity.
Exactly. But wait, if this ice bulldozer was so heavy that it scraped away all the dirt and soft rock to gouge out those muddy basins, why is Cash's Ledge still there?
That is the big question.
Yeah, why didn't a mile-thick glacier just shear almond rock totally flat?
It all comes down to the fundamental physics of the rock itself. Compressive strength and molecular structure.
Because it's granite.
Right. That magma that cooled millions of years ago created a material that was simply too hard to be completely crushed, even by a mile of ice.
Oh, wow.
The ice sheet acted exactly like your bulldozer on the weaker materials. It pulverized the soft sedimentary rocks and gouged out the deep valleys.
But when it hit Cash's Ledge,
It met a force that refused to yield. The ice was literally forced to ride up and scrape over the top of the rock.
it just rolled over.
Yeah. It polished the peaks, it sheared off loose edges, sure, but the core of the mountain stood strong.
So it survived the ultimate geological test of strength. It's almost like a stubborn knot in a piece of wood that the sander just can't smooth down.
That is a perfect analogy. The soft wood was sanded away into valleys, leaving the hard knot protruding. And then, about 10,000 years ago, the climate began to warm.
And the glacier melted.
Right. That massive ice sheet began its long retreat. And when a glacier that covers half a continent melts, it releases an unimaginable volume of water.
Global sea levels rose.
Dramatically. The rushing seawater flooded the coastal plains, poured into those deep valleys the glacier had carved, and turned them into the dark, muddy basins we see today,
And eventually, it swallowed the ancient granite mountain entirely.
leaving us with a towering underwater rock fortress. And this hard, unyielding mountain is the absolute foundational key to why life exists there today.
Because things can't grow on the mud.
Exactly. The physics of marine biology mean that foundational life giant sponges, anemones, kelp, they cannot grow on soft, shifting mud.
Right, if a tiny kelp spore tries to grab onto the mud, the first strong current would just blow it away into the dark.
Exactly. They desperately need a hard, stable, immovable foundation. Because the glacier failed to destroy the ledge, it left behind the perfect stage for life to grab onto.
Okay, that makes sense architecturally. We have an indestructible rock for things to sit on, but, well, a rock alone doesn't create a rainforest.
No, it certainly doesn't.
Like if I put a boulder in a swimming pool, I just have a wet boulder. Something has to be feeding this ecosystem. Something brings the energy.
And you've hit on the most crucial part of the system. If the granite is the physical foundation, the ocean currents are the biological engine that brings it to life.
The engine, okay.
To understand this, we have to look at the Gulf of Maine as a whole. It's structured somewhat like a giant semi-enclosed sea walled off from the open Atlantic.
Oh.
Because of its shape and the rotation of the Earth, it has a massive river of water circulating around it in a counterclockwise circle.
Like a giant whirlpool.
Kind of.
Hmm?
Oceanographers call it the Maine coastal current. It's a freezing, fast-moving flow of water traveling deep along the ocean floor.
And let me guess. This deep freezing river is on a direct collision course with our 32-mile granite wall.
It is a direct hit. And here's why that matters. Because this water is traveling deep down along the bottom, it is absolutely packed with essential deep-sea nutrients.
Like what kind of nutrients?
Massive concentrations of nitrogen, phosphorus, iron. It's basically natural fertilizer.
Formed from stuff breaking down in the dark.
Exactly. Dead plankton, sinking fish scales, marine snow. It all breaks down in the depths over thousands of years.
But normally those nutrients just sit trapped in the dark where there's no sunlight, right?
Right. And without sunlight, marine plants can't use the fertilizer to grow. The nutrients are stuck in the basement, but the sunlight is up on the roof.
Ah, I see.
But when this fast-moving deep current slams into the steep vertical walls of Cash's Ledge, the physics of fluid dynamics take over.
The water can't go through the solid rock.
No, and there's too much water behind it to flow backward. So the path of least resistance is up. It's forced violently upward along the cliff face.
It has nowhere to go but up the mountain.
Marine scientists call this process upwelling. And at Cash's Ledge, it acts exactly like a giant, high-speed nutrient elevator.
A nutrient elevator.
It drags millions of gallons of that freezing, fertilizer-rich water from the muddy basins all the way up to the highest peaks. And what is waiting at Ammon Rock, just 30 feet down.
The sunlight. You're bringing the basement fertilizer straight up to the sunny roof.
Exactly. But upwelling isn't the only trick up the ledge's sleeve. You mentioned in the opening story a wave moving under the water.
Right, I was going to ask about that. How on earth can there be waves under the ocean?
It sounds impossible, doesn't it?
Yeah. I mean, when I think of waves, I think of wind blowing across the surface, making swells that crash on the beach. How do you have an invisible wall of force beneath a totally flat surface?
It all comes down to density. During the spring and summer, the water in the Gulf separates into highly distinct layers.
Because of the sun?
Yes. The sun beats down, heating the top layer. Warm water expands slightly, making it less dense or lighter.
Right.
But underneath that surface layer, the deep water remains freezing cold and incredibly dense. So you have two completely different layers of water sitting right on top of each other.
Separated by a boundary line.
A sharp boundary called a thermocline.
Oh, I get it. It's a density issue. It's like when I make homemade salad dressing.
Okay, tell me about the dressing.
Well, if I pour oil and vinegar into a glass bottle, they separate, right? The oil sits on top because it's lighter.
Exactly.
And if I tilt or gently shake that bottle, the surface of the oil might stay totally flat against the glass, but the boundary where the oil meets the vinegar inside is sloshing around. The waves are happening inside the liquid.
That oil and vinegar analogy is flawless. That is exactly what is happening in the ocean. The warm surface water is the oil, and the freezing deep water is the vinegar.
Okay, so what shakes the ocean's bottle?
The powerful ocean tides. Driven by the gravitational pull of the moon, they push millions of tons of this layered water horizontally across the ocean.
And when it hits the mountain?
It disturbs that boundary line between the warm and cold layers. It forces the layers to buckle and heave over the rock, creating massive hidden swells that travel entirely underwater.
Internal waves.
Internal waves, completely invisible to a boat on the surface, but down below, they are incredibly powerful forces of nature.
Just rolling over the ledge.
Right. And as they do, they force the warm water down and pull the freezing deep water violently up. These waves can literally drop the temperature of the water around the mountain by 9 to 11 degrees Celsius in minutes.
That is a staggering temperature drop. That would be like walking through a warm, sunny park and suddenly someone opens the door to an industrial meat freezer.
Just an instant plummet.
A massive shock to the system.
It is, but ecologically, it's the lifeblood of the forest. The sheer physical force of these internal waves acts like a giant oceanic blender.
So they keep things moving.
They constantly stir the water column, If the water was still, the surface life would consume all the nutrients and the rest would sink back to the dark bottom.
Ah, so the internal waves ensure the fertilizer never settles.
Exactly. They keep it perfectly mixed with the sunlight, feeding the whole ecosystem in a continuous loop.
Okay, let's actually pause right here. We've talked about glaciers and currents and internal waves on this huge planetary scale.
The big picture.
Yeah, but I want us to really feel what this nutrient elevator and this giant blender are like from a micro perspective. Let's zoom all the way in.
Okay, how small are we talking?
Imagine you are a single drop of water. Or even better, a microscopic crustacean, a tiny creature called a copepod.
Just a speck of dust suspended in the water.
Exactly. Right now, you are hundreds of feet deep, down in the muddy basin alongside the base of Cassius Ledge. It is pitch black. No sunlight has touched this mud for thousands of years.
And it's bone-chillingly cold.
Right. The water around you feels heavy, dense, and still, but slowly you feel a subtle pull. The deep coastal current has caught you.
Sweeping you along.
You start drifting horizontally, moving faster and faster until suddenly the current slams against a solid, unyielding wall of ancient granite. You're caught in the upwelling.
Getting pushed vertically up the cliff.
The sheer kinetic force sweeps you violently upward. As you rise, the crushing pressure of the deep ocean starts to lighten. The temperature fluctuates wildly, swinging from freezing to warm and back again as those internal waves toss you across the thermocline.
The blender in action.
And then the inky darkness gives way to a faint, glowing green twilight. Within seconds, that twilight becomes a blinding, brilliant burst of sunlight.
You've reached the roost.
Yes. And as the sunlight hits that fertilizer-rich water you rode up with, a chemical and biological miracle happens all around you. Billions upon billions of microscopic marine plants' phytoplankton absorb that light.
They undergo rapid photosynthesis.
They multiply instantly. It's a swirling, chaotic, neon green explosion of life. You're tumbling head over heels in this thick green cloud of food. The current sweeps you up over the jagged peak.
And the golden forest appears.
A vast, towering forest. Giant rubbery blades of kelp like velvet curtains as you rush headlong into the canopy. You dodge the snapping jaws of a darting silver fish, only to be swept downward straight toward the rock face.
And something is waiting there on the rock.
Clinging tightly to the granite is a creature that looks like a fluffy white cauliflower, but it's actually a plumose sea anemone.
With its tentacles out.
Thousands of microscopic, feathery, stinging tentacles in the rushing current, just waiting to catch a speck of dust like you.
That journey of the copepod perfectly illustrates the fundamental truth here. The physical mountain physically generates the biology.
Because it forces the water into the light.
Right. The upwelling creates the phytoplankton blown. The balloon feeds the copepods feed the fish. And all that intensely concentrated food allows the golden forest you described to grow to such an unbelievable size.
So let's focus on that forest, because we keep using the word forest, and I think that sets up a certain expectation, you know.
It paints a very specific picture.
Yeah. When I think of a forest, I picture towering oak trees or pines dropping needles, deep dirt, roots digging down to find water. But this underwater forest operates on completely different rules.
Entirely different rules.
Because it's made entirely of kelp.
Yes. And it's crucial to clarify right up front that kelp is not a plant.
Oh, wait, really?
Yeah, it looks like a plant and it acts somewhat like one, but biologically it's a highly advanced type of large brown algae.
Okay, algae.
Specifically, the dominant species at Cassius Ledge is Saccharina latissima, commonly known as sugar kelp.
Sugar kelp, I like that.
Now, terrestrial plants, the ones in your backyard, they require a vascular root system.
They need roots in the dirt.
Right, they act like straws to drink water and absorb minerals. But as we established, there is absolutely no dirt on Ammon Rock. It is solid, polished granite.
Which presents a huge engineering problem. How does a massive organism stay permanently attached to a slippery rock, especially when those violent internal waves are constantly trying to rip it away?
It's not easy.
I mean, if I were standing on a rock during a hurricane and a wall of wind hit me, I wouldn't be able to just hold on with my bare hands. I'd fly away instantly.
Exactly. The grip strength needed is unbelievable.
So how does the kelp do it?
It uses an evolutionary masterpiece of design. To survive the hydrodynamic drag, the kelp develops a highly specialized base called a holdfast.
Holdfast?
A holdfast looks less like roots and more like a tough, tangled knot of rubbery fingers.
Oh, weird.
These fingers wrap themselves around the microscopic bumps and crevices of the granite, and they excrete a natural biological adhesive that glues the algae to the stone with incredible tensile strength.
So it literally glues itself down.
Yes. And once anchored, it doesn't act like a straw. It doesn't pull nutrients from the rock. The kelp just absorbs the nitrogen and phosphorus from the upwelled water directly through its cellular walls as the current washes over it.
That is brilliant. It uses the rock purely for stability and lets the internal waves deliver the food directly to its skin.
Exactly.
So it has a super strong anchor. What does the rest of the organism look like? If it's acting like a forest canopy, how big does it get?
The scale is massive. Growing straight up from the holdfast is a flexible, rubbery stem called a stipe.
A stipe.
Think about a terrestrial tree. A pine tree has a rigid wooden trunk to hold itself up against gravity. But a rigid trunk underwater would be a disaster.
Because the waves would just snap it like a twig.
Exactly. So the kelp stipe evolved to be incredibly elastic, packed with a flexible carbohydrate called alginate. When an internal wave hits, the kelp doesn't fight the force.
It just goes with the flow.
It bends entirely flat against the rock, letting the water rush harmlessly over it. And the moment the wave passes, it springs right back up toward the light.
That's amazing.
And these stipes can grow up to 24 feet tall.
24 feet.
Yes.
Yeah.
And at the very top of the stipe, spreading out into the water, are broad, long, golden brown structures called blades.
The equivalent of the leaves.
Right, but biologically superior for this environment. They act like highly efficient, flexible solar panels. They spread out wide near the surface to capture the sunlight.
Because they need to photosynthesize.
Yes, and because kelp is brown algae, it contains a special pigment called fucoxanthin. It's highly efficient at absorbing the specific blue-green wavelengths of light that penetrate deep water.
So it grabs the light, grabs the fertilizer from the water, and makes food.
Exactly. And because the water here is so clear and so packed with fertilizer, the sugar kelp grows to staggering proportions. It creates a complete three-dimensional environment structurally identical to a tropical rainforest.
You have the canopy at the top, the shady understory along the stems or stipes, and a populated floor down by the holdfasts.
It's an entire world. And the sheer scale and density of this forest is what makes Cash's Ledge a global anomaly.
It's not just a healthy patch of seaweed.
No, it's an extreme outlier. Cash's Ledge is home to the deepest, densest, continuous cold water kelp forest on the entire Atlantic seaboard.
Wow.
Marine biologists have measured the biomass, and the kelp forest here is up to 150 times denser than the typical kelp forests found near the coast of Maine.
150 times denser. That is an absolute powerhouse.
It really is.
So, looking at the big picture, we have successfully built the house. We have the ancient granite foundation, the internal wave plumbing system bringing in the food, and the towering, flexible kelp providing walls and a roof.
The physical architecture is set.
Right. Now we have to talk about who actually lives inside this house. And right here, I want to make a special note to everyone listening. The animals living at Cash's Ledge are so unique and bizarre, we literally cannot fit all their stories into this one journey.
We'd be here for days.
Exactly. So I promise you, many of these creatures are going to get their very own dedicated episodes of Saltwater Stories in the future. We'll explore their hunting strategies and life cycles in detail later.
But for today, we're just looking at how they interact with the place itself.
Right, taking a high-level glimpse at the actors on this stage to see how they fit into the ecological magic of the ledge.
And what a cast of actors it is. When you have a habitat with 150 times the kelp density, it acts as an incredible multiplier for life.
Because of all that food and all those hiding spots.
Yes, the 24-foot canopy creates an endless maze of protection. Cash's Ledge actually supports up to 305 times more fish biomass than heavily fished coastal areas.
Wait, over 300 times more?
Yes. If you took a cubic acre of coastal water and weighed all the fish inside it, and then weighed the fish at Cash's Ledge, the ledge would have over 300 times more sheer mass of fish.
That is unbelievable.
When scuba divers descend into the kelp here, they often describe it as entering a literal fish tornado.
A fish tornado?
You're not just seeing a fish here or there. You're engulfed in swirling schools of thousands of silver pollock and herring darting in every direction.
Swirling around inside a golden forest, but hidden inside that silver mass are some highly specialized permanent residents, right?
Yes, animals that have altered their biology for this exact spot.
Like our friend from the opening story, the red cod.
The red cod is a perfect example of localized evolutionary adaptation, or phenotypic plasticity.
Okay, big words. What does that mean?
Well, the Atlantic cod is a very famous fish, Usually cod that live out in the open ocean or over sandy bottoms are a mottled olive green or grayish color,
To blend in with the deep water.
right, to avoid predators. But the subpopulation of cod that live permanently on Cash's Ledge have adapted to their specific localized architecture,
They spend their whole lives in the shady understory.
weaving among the golden stipes and the red algae on the granite. Over time, they've adapted to become a striking, vibrant rust-red color. Their pigment cells match the red algae perfectly.
It's incredible. They essentially put on a ghillie suit made of red algae.
Exactly. And it's not just their color. Scientists noted that the cod living strictly on the ledge tend to have slightly shorter snouts and deeper, more muscular bodies than their open ocean cousins.
Why is that?
It makes them perfectly shaped for tight, agile maneuverability. They don't need to swim in long, straight lines. They need to aggressively twist and turn around sharp granite boulders to hunt for crabs without bumping their noses.
So they evolved to be these highly maneuverable stealth ninjas of the kelp forest.
Basically, yes.
But as cool as the red cod is, I think my favorite resident of Cash's Ledge, and maybe one of the strangest fish in the ocean, is the Atlantic wolffish.
Oh, the wolffish.
Just the name wolffish sounds intimidating.
It's an incredible creature, and it certainly looks the part of a predator. It has a long, muscular, almost eel-like body that can grow to 5 feet long, paired with a massive, blocky, heavily armored head. But its most famous feature is its teeth. It has huge, protruding canine teeth in the front that look like little tusks, and massive, flat, crushing molar teeth in the back.
Oh, wow. But it doesn't use those tusks to chase down fast fish, does it?
No, it uses them to pry hard-shelled prey off the rocks. It hunts green sea urchins, thick-shelled crabs, and sea snails. It has a bite force that is just unbelievable, effortlessly crushing thick calcium carbonate shells into powder with those back molars.
A 5-foot armor-headed sea monster that crushes solid shells for breakfast. But they actually have a surprisingly soft side, right? They aren't just mindless crushing machines.
They display some of the most dedicated parental care in the ocean. When the female wolffish lays a large bowling ball-sized cluster of eggs deep inside a granite cave, the father immediately takes over.
Dad mode activated.
He wraps his long body entirely around the egg mass, using himself as a living shield. And he fiercely guards them from crabs and other fish for months until they hatch.
Wow, months.
He's so utterly dedicated that he will entirely stop eating during those months, relying solely on his stored energy just to ensure he never leaves their side.
That is just beautiful. A fierce, urchin-crushing predator that is secretly the ocean's most devoted dad.
It really is.
But you just mentioned that they eat green sea urchins, and that brings up a massive ecological mystery about Cash's Ledge, the mystery of the missing urchins.
This is perhaps the most important ecological piece of the entire puzzle. It's a classic example of a trophic cascade.
Okay, tell me more.
If you study coastal kelp forests along California or closer to shore in Maine, you'll often find them swarming with green sea urchins. Urchins are basically the underwater equivalent of locusts or lawnmowers.
They love to eat kelp.
And if their population grows unchecked, they swarm the forest. They chew right through the base of the kelp holdfast.
Oh, no.
When the holdfast is severed, the entire 24-foot kelp canopy simply detaches and floats away into the ocean, leaving bare, empty rock behind. Scientists call these urchin barrens.
A complete collapse of the ecosystem.
Exactly. But when marine biologists studied the peaks of Ammon Rock, they noticed something strange. Despite having 150 times more kelp for the urchins to eat, the urchins are almost completely missing.
So why aren't the underwater lawnmowers out there clear-cutting the rainforest? What's stopping them?
The wolffish, alongside the massive mature cod. The wolffish acts as what ecologists call a keystone species.
Like the keystone in an arch.
Exactly. The single stone at the top of a Roman arch. If you remove it, the bridge collapses. The wolffish is the keystone holding Cash's Ledge together.
By constantly patrolling the granite and eating the urchins.
Yes, using that massive bite force to crush the few urchins that do manage to settle. They keep the population artificially low. They act as the fierce, dedicated guardians of the forest.
And without them keeping the grazers in check, the urchins would multiply, sever the holdfasts, and the golden forest would be destroyed.
It would all float away.
It's an incredibly delicate, perfect balance. The ancient granite provides the foundation for the kelp. The kelp provides the architecture that hides the fish. The fish aggressively hunt the urchins. And by eating the urchins, the fish ensure their own home isn't destroyed.
A perfectly closed loop of survival.
But the big fish and the towering kelp aren't the only things clinging to the rock, are they? If I swam down past the fish tornado, past the red cod, and gently pushed the golden kelp blades aside to look at the sheer rock face beneath what is actually covering the granite.
You'd be shocked to find you wouldn't even see the gray color of the granite.
Really?
The rock is completely encrusted in a thick, vibrant, living carpet of invertebrate animals without backbones. Because the upwelling delivers such a constant stream of phytoplankton, those cliffs are prime real estate for filter feeders.
It must look amazing.
It's a kaleidoscope of texture and color. You have those plumose sea anemones stretching out their stinging tentacles, making the rocks look like fields of pristine white cauliflower.
And what else?
Growing right next to them are massive, bright yellow mounding sponges, roughly the size of soccer balls. These sponges are basically biological water pumps.
Filtering the water.
Yes, tirelessly drawing the freezing seawater into their porous bodies, stringing out the microscopic food, and expelling clean water. And Cash's Ledge is also home to an incredibly rare, brightly colored blue sponge found almost nowhere else in the Gulf.
So when you combine the golden kelp, the red algae, the white anemones, and the yellow and blue sponges, you have an invertebrate garden that looks like an alien world.
It rivals a tropical coral reef in sheer beauty and biodiversity.
Okay, so we have this isolated magical mountain range packed with all this life. But what I find most profoundly moving about Cash's Ledge is that it isn't a walled-off kingdom.
No, it's deeply connected.
Right. It doesn't hoard all this biological wealth for itself. It sends its energy outward to support the rest of the world. Let's look at how this one submerged rock connects to the broader Atlantic Ocean.
Which brings us to the birds.
Yes, this brings up a wonderful scientific mystery about one of my absolute favorite birds. For years, scientists working in Maine had a massive puzzle regarding the Atlantic puffin.
The comical little seabirds with the bright orange striped beaks.
Exactly. Every summer, they come to the coastal islands to lay their eggs and raise their chicks. But when autumn ended and the freezing winter arrived, the puffins completely vanished.
No one knew where they went.
Right. How did scientists finally figure out the secret?
It was a brilliant piece of ecological detective work. Researchers managed to attach incredibly tiny, lightweight tracking devices, called geolocators, to the legs of several puffins.
Not heavy GPS trackers, right?
No, these are ingenious. They record the exact time of sunrise and sunset every single day. This allows scientists to calculate the bird's latitude and longitude based on the angle of the sun.
That is so smart.
And when they recovered the devices a year later and downloaded the data, the map revealed an astonishing secret.
They weren't flying south to a warm beach, were they?
Not at all. They were flying straight out into the open ocean, directly into the teeth of the most brutal, freezing winter storms, spending the entire harsh winter floating on the rolling, freezing waves directly above Cash's Ledge.
But logically, that makes no sense. Why would a small bird brave a freezing storm, risking hypothermia, when it has the wings to fly somewhere warm? What's the draw?
The draw is the absolute guarantee of food. You have to remember the physical engine of the ledge, that giant underwater blender, the internal waves and the upwelling.
It's still working in the winter.
Even in the dead of winter, when the surface is dark and churning with storms, the main coastal current is still flowing. The upwelling is still forcing nutrients up.
So it's a continuous, reliable winter buffet.
Exactly. The puffins evolved to know that while the rest of the ocean becomes a barren desert in winter, the water above Cash's Ledge will always, without fail, provide enough small fish and plankton to keep them alive.
The mountain provides for them.
It sustains them through the hardest months of the year.
That is just incredible to think about. A mountain made of magma-cooled rock, hidden underwater, is directly responsible for keeping flocks of seabirds alive in the sky.
It's an invisible lifeline.
And it's not just these tough little winter wanderers that visit, right? When the seasons change and the water warms up, the summer brings some truly gentle giants.
Oh, absolutely. When the spring and summer sunlight hits that constantly upwelled fertilizer, the resulting phytoplankton blooms are so massive that they attract the largest animals on planet Earth.
Like the 20-foot basking shark from our opening story.
Yes. Basking sharks are the second largest fish in the world, and they come specifically to Cash's Ledge. They cruise along the surface using ram ventilation,
Just swimming forward with their mouths wide open.
pushing thousands of gallons of water over their gill rakers to filter out the rich plankton soup. You also have massive pods of humpback whales arriving from their migrations.
Whales.
Highly intelligent whales that use the dense fish populations to execute complex, cooperative hunting strategies.
Like the bubble nets.
Yes. A group of humpbacks will dive deep below a school of herring and swim upward in a shrinking circle, blowing air from their blowholes to create a cylindrical bubble net.
And the bubbles act like a physical wall, trapping the panicked fish.
Then the entire pod of whales lunges straight up through the center of the bubble cylinder, mouths open, consuming thousands of fish in a single gulp.
That is awe-inspiring.
And perhaps most importantly, the massive blooms of copepods attract the North Atlantic right whale. This is one of the most critically endangered marine mammals on the planet, with only a few hundred individuals left.
And they travel specifically to the ledge to gorge on the plankton.
They do. So when you look at the puffins, the sharks, and the whales, you realize Cash's Ledge isn't just an isolated habitat. It acts as a beating ecological heart that pumps life and energy to migratory animals across the entire ocean.
A beating heart, but just like a real heart, it's fragile and it needs to be protected. Now, for hundreds of years, this place was completely safe from human impact. How did a mountain hidden in a highly trafficked ocean protect itself for so long?
It protected itself with its own formidable, rugged geography.
Right.
For centuries, humans have been aggressively fishing the Gulf of Maine. It's a vital part of the region's history. But traditional fishermen, going back to the days of sailing schooners, knew to entirely avoid Cash's Ledge.
Because of the granite peaks?
The sheer vertical cliffs and jagged rocks formed a natural, impenetrable fortress. If a fishing trawler tried to drag its nets near Ammon Rock, the unyielding granite would instantly snag the ropes and rip the expensive nets to absolute shreds.
Too expensive and dangerous to even attempt.
Exactly. Because of that physical defense, the delicate kelp forest, the fragile sponges, and the massive cod populations were left completely alone. They grew wild and pristine, acting as a time capsule of what the ocean used to look like.
But the tragic reality of human engineering is that technology always finds a way to overcome natural fortresses, doesn't it?
Unfortunately, yes.
The rocks couldn't protect the ledge forever. What changed?
In the 1980s, industrial fishing vessels developed a new type of gear called rock hopper nets. These were massive, heavy trawl nets equipped with giant, heavy-duty rubber discs or rollers along the bottom edge.
Oh, no.
Instead of dragging directly on the bottom and snagging, the rollers allowed the nets to literally bounce and roll directly over the jagged peaks of Cash's Ledge.
Crushing everything in their path while keeping the net intact. That sounds physically devastating to an ecosystem built on fragile architecture.
It is biologically catastrophic. When a heavy rock hopper net is dragged across the seafloor, it acts exactly like a mechanical clear-cutting machine in a forest.
Smashes right through it.
It crushes the delicate, slow-growing yellow and blue sponges. It smashes into the rocky dens where the wolffish are fiercely guarding their eggs, destroying the next generation.
And it violently rips up the kelp holdfasts,
Completely leveling the three-dimensional canopy that the juvenile fish desperately need to hide from predators.
so it's just total destruction.
Scientists estimate that if a complex invertebrate community of sponges and anemones is severely crushed by a trawl, the physical damage is so profound that it could take over 200 years for that exact patch of rock to fully recover.
200 years, that is heartbreaking. It's like bulldozing a cathedral.
It really is.
But physical nets aren't the only threat creeping into this ecosystem anymore, are they? There's a much larger, entirely invisible threat altering the chemistry of the water itself.
Yes, and this is the insidious challenge of global climate change. The Gulf of Maine is currently warming at an incredibly fast rate, faster than almost 99% of the rest of the ocean's surface on the planet.
Wow, 99%.
Yes. The complex currents that normally bring cold water down from the Arctic are shifting. And remember the biology of the forest. The sugar kelp that forms this majestic canopy is strictly a cold water species.
It evolved to thrive in freezing temperatures.
So as the ambient temperature slowly heats up, the kelp begins to experience severe physiological heat stress. Its cellular growth slows down, the tissue weakens, and the organism becomes highly vulnerable.
And nature abhors a vacuum. When the towering king of the forest gets weak, I imagine other opportunistic things try to rush in and take its throne.
Exactly. The warming water has opened a thermal doorway for invasive species that historically couldn't survive in the freezing Gulf.
Like what?
One of the most aggressive is an invasive red algae that forms a thick, bushy mat on the rocks. Marine scientists casually refer to it as the red carpet, or turf algae.
The red carpet.
This turf algae creeps aggressively across the granite, quickly monopolizing all the bare rock space where new kelp holdfasts would normally try to attach. It chokes out the kelp's ability to reproduce,
And because it's short and bushy, it completely eliminates the tall canopy.
meaning the juvenile cod have nowhere to hide. Furthermore, there is a tiny, crusty colonial animal called a bryozoan.
A bryozoan.
These tiny creatures thrive and multiply exponentially in warmer water. They encrust themselves directly onto the wide golden blades of the living kelp. They create a hard, calcium-like shell over the kelp tissue.
But wait, remember how the kelp survives the internal waves by being rubbery and flexible?
Exactly. The bryozoans turn the flexible kelp blades stiff, heavy, and brittle. So when those powerful internal waves roll through, the stiffened kelp can no longer bend. It simply snaps off and dies.
The invisible heat is slowly mechanically changing the entire neighborhood from the bottom up.
It is a profound shift.
Okay, I have to admit, that feels heavy. It feels like this magical, isolated place is under relentless siege from all sides. From massive nets tearing it down, to invisible heat and microscopic invaders choking it out.
It's a precarious situation.
But I know this isn't a story of despair. This is Saltwater Stories, and there is always hope when people care enough to act. What is actively being done to save the Yellowstone of the North Atlantic?
There is immense actionable hope, and it stems directly from the biological density we discussed earlier. Because this place is so miraculously dense with life, it is incredibly stubbornly resilient.
So it can bounce back.
Yes. Several years ago, temporary fishing closures were put in place to stop the rockhopper nets from dragging over the highest peaks of Ammon Rock. And the ecosystem proved a vital point. If we simply remove the mechanical damage and leave nature alone, the ledge has the capacity to bounce back beautifully.
The kelp regrows, the sponges expand, the cod multiply.
But temporary rules are just that, temporary. They can be reversed. Right now, an unprecedented coalition of marine scientists, conservation groups, and policymakers are fighting to designate Cash's Ledge as a permanent national marine sanctuary.
A national marine sanctuary, if they succeed, it changes everything, right?
It means the federal government will legally, permanently protect this mountain range. It will become the equivalent of a permanent underwater national park, safeguarding it from physical destruction forever.
Let's talk about why that sanctuary status matters so much, because we aren't just trying to save a cool spot for scuba divers. Why does locking down this specific 32-mile ridge matter for the entire ocean?
It matters because of a concept in ecology known as source sink dynamics. Cash's Ledge is recognized globally as a hope spot.
A hope spot. I love that.
If we can protect this highly concentrated place, its incredible biodiversity will act as a permanent, resilient seed bank for the rest of the ocean. Think of it as a massive biological engine.
The undisturbed kelp captures carbon.
The mature cod grows safe and strong, laying millions of eggs. The wolffish guard their dens in peace. And eventually, the sheer carrying capacity of the mountain will overflow.
It'll spill over.
Yes. There will be so many fish and so many billions of microscopic larvae caught in the main coastal current that they will physically spill over the edges. They'll be swept out into the broader Gulf, acting as a biological resupply ship.
Helping to heal and repopulate the heavily depleted coastal areas hundreds of miles away.
By fiercely protecting this one hidden mountain, we are actively generating the life needed to save the entire sea.
That is just a profoundly beautiful thought. A hidden seed bank, locked away in an underwater fortress, quietly waiting to heal the world.
It truly is.
Let's recap this incredible, expansive journey we've been on today. We started millions of years ago, deep underground, with boiling magma slowly cooling into indestructible granite.
We watched a colossal Ice Age glacier fail to crush that stone, leaving behind a jagged underwater mountain range.
We felt the physical rush of the freezing main coastal current slamming into the rock wall, creating massive, invisible internal waves that drive a high-speed nutrient elevator.
Pulling deep-sea fertilizer right up into the sunlight.
And from that interlocking engine of water and stone, we discovered a golden, swaying underwater rainforest, a three-dimensional canopy, a safe haven for stealthy red cod, fierce fatherly wolffish, and a breathtaking carpet of white anemones and rare blue sponges.
Cash's Ledge truly is a masterpiece of natural engineering.
A beating biological heart hidden 80 miles offshore, feeding everything from tiny storm-tossed puffins to gigantic migrating whales.
It's a perfect, humbling reminder that just because a place is hidden deep beneath the waves, far from human eyes, it doesn't mean it isn't completely vital to the health of our planet. The invisible engines of the ocean are what keep the visible world alive.
Exactly. I want to say a sincere, heartfelt thank you to you, our listener, for coming along on this incredibly deep journey with us today. It's a privilege to explore a place that very few humans will ever get the chance to see with their own eyes, but that we can all hold in our imaginations.
It's been wonderful sharing it with you.
Before we go, I want to leave you with a final provocative thought to carry with you. Think about the environment nearest to you. It might be the ocean, a local lake, a deep forest, or even just a quiet patch of trees in a park right near your home.
Just whatever piece of nature is close by.
Today, we've seen how a single, isolated mountain, hidden entirely underwater in the freezing Atlantic, generates a massive web of life that physically travels across the globe. It feeds birds that fly the skies and whales that cross the oceans.
An invisible web.
So what invisible connections might be happening right in your own backyard? What tiny engines of nature are quietly working, entirely unseen, keeping the world alive without you even noticing? See you next time on Saltwater Stories.